In episode 56, titled Multicollinearity, How to Spot It and What to Do About It, the aim is to handle multicollinearity before it distorts interpretation and destabilizes your results. Multicollinearity is one of those issues that can hide inside a model that seems to perform well, only to surface later as confusing coefficients, unstable explanations, and wildly different conclusions when you retrain on slightly different data. The exam cares because multicollinearity is not a mathematical curiosity. It is a real-world failure mode that shows up whenever you measure the same concept multiple ways or create many derived features from a common source. In operational settings, it can turn a clear story into a shaky one, because a model that cannot decide which correlated feature deserves credit will spread influence unpredictably. If you learn to spot it and address it early, you improve both stability and communication. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Multicollinearity means that predictors share strong overlapping information, so the model sees multiple features that are telling it essentially the same thing. This overlap does not necessarily hurt raw predictive accuracy because the model can still use the shared signal, but it can inflate uncertainty and make individual coefficient estimates unreliable. In a regression-style model, the coefficient on a feature is meant to represent the effect of that feature holding others constant. But if several features move together, holding others constant becomes an unrealistic thought experiment. The model can then assign weight to one feature in one sample and to a different correlated feature in another sample, producing unstable interpretations even when overall predictions are similar. The exam often tests this by presenting a model with counterintuitive coefficients and asking what issue might explain it, and multicollinearity is a common correct diagnosis. When you define it clearly, you also clarify why it matters. It undermines attribution, not necessarily prediction. The symptoms are often visible before you compute anything, and the two classic ones are unstable coefficients and surprising sign flips. Unstable coefficients show up when small changes in the data, such as resampling, adding a few records, or slightly changing the time window, cause large changes in coefficient magnitudes. Sign flips show up when a feature you expect to have a positive relationship ends up negative in the fitted model, or vice versa, even though pairwise relationships suggest the opposite direction. These symptoms can be especially confusing because the overall model may still fit well, so it feels like the model is wrong even when it is simply struggling to distribute weight among redundant predictors. The exam likes these symptoms because they can be described in words without requiring computation. And your job is to recognize that the issue is not necessarily the feature's true direction, but the overlap with other features. When you see instability and sign surprises together, multicollinearity should be high on your list of explanations. The causes are usually mundane, which is why multicollinearity is common in real datasets. Duplicates happen when the same field is ingested from two sources under different names or slightly different formats, leading to near-identical predictors. Derived fields happen when you create ratios, rolling averages, or normalized versions that are mathematically linked to the original, causing strong dependence between features. Correlated measurements happen when multiple sensors or processes measure related aspects of the same underlying factor, such as different indicators of load, activity, or exposure. Even well-intended feature engineering can create redundancy,
especially when you generate many variants of the same concept to let the model decide. The exam expects you to recognize these sources and to suspect multicollinearity when you see many fields that sound like variations of a single idea. When you narrate causes clearly, you are emphasizing that multicollinearity is often created by pipeline and feature design choices, not by mysterious data behavior. A conceptual correlation check is a practical way to find redundant feature clusters because highly correlated predictors tend to form groups that move together. You do not need to compute a full matrix in your head on the exam. You need the reasoning that if two or more predictors track the same underlying driver, they will show strong association and will compete for explanatory power. In many cases, redundancy is visible from field definitions alone, such as two metrics that are both derived from the same numerator and denominator, or two timestamps that differ only by time zone conversion. Correlation checks also help you see indirect redundancy, where feature A correlates with feature B and feature B correlates with feature C, creating a cluster even if A and C are less directly correlated. The exam may phrase this as high correlation among predictors, and the right response is to treat it as a stability and interpretability issue rather than as a reason to celebrate strong relationships. When you identify clusters, you are setting up the next decision: remove, combine, regularize, or reduce dimension. Variance inflation factor, often abbreviated VIF, provides an intuition for how collinearity inflates variance and uncertainty in coefficient estimates. The key idea is that when a predictor can be predicted well from other predictors, the model has difficulty isolating its unique contribution, so the coefficient estimate becomes noisy. High VIF values conceptually mean that the uncertainty around the coefficient is inflated, leading to wide intervals and unstable signs, even when the overall fit looks acceptable. You do not need to memorize a specific threshold to use the intuition correctly on the exam. You need to recognize that high VIF is a signal that predictors are redundant and that coefficient interpretation is unreliable. VIF is essentially a warning that the model is trying to separate signals that are not separable given the data. When you explain VIF intuitively, you are explaining why multicollinearity is not just correlation. It is correlation that makes attribution unstable. When interpretation matters, the best response is often to remove or combine correlated features so the model has a clearer set of distinct concepts. Removing a feature can be appropriate when it is a redundant proxy for a better defined concept, or when it adds little incremental information beyond another feature. Combining features can be appropriate when both features matter conceptually, but their separation is not meaningful, such as when you create an index or composite that represents the shared underlying factor. The goal is to reduce redundancy so that remaining coefficients have clearer meaning and more stable estimates, which supports explanation to stakeholders and supports more reliable causal narratives. The exam often frames this as choosing a remedy that improves interpretability, and simplification is usually the correct theme. When you remove or combine, you should do it deliberately, based on domain meaning and evidence of redundancy, rather than arbitrarily dropping variables. When prediction matters more than coefficient meaning, regularization is often the preferred tool because it can manage multicollinearity without requiring you to hand-select one feature from a redundant set. Regularization discourages extreme coefficients and can spread weight more stably, reducing variance and improving generalization, especially in high-dimensional settings. It also allows you to keep multiple correlated predictors when you believe they collectively capture a concept, but you do not need to attribute unique causal meaning to each one. The exam expects you to understand this trade-off. Regularization can improve predictive stability, but it does not magically make individual coefficients interpretable as causal effects. In other words, regularization can stabilize prediction under multicollinearity, but it does not solve the attribution problem in the way feature removal or conceptual consolidation can. When you choose regularization, you are choosing operational performance and robustness over interpretive purity. If many features correlate strongly together, dimensionality reduction can be appropriate because it represents shared variation in a smaller set of components. This is especially useful when your predictors form clusters around latent factors, such as overall activity, load, exposure, or risk, and the raw features are multiple noisy measurements of the same underlying drivers. By projecting into a smaller space, you reduce collinearity and can create more stable inputs for downstream models. The trade-off is that components can be harder to interpret directly, which matters if your goal includes explaining which concrete business concept drove a decision. The exam often tests whether you can recognize this trade-off and choose reduction when the priority is stability and generalization rather than fine-grained attribution. Dimensionality reduction is not a first move in every case, but it can be a sensible response when redundancy is widespread and feature selection becomes arbitrary. When you narrate this option, you are emphasizing that the structure is real, but the representation is too detailed and overlapping. One important caution is to avoid dropping features that represent critical business concepts without thought, because simplification can accidentally remove the very signal or accountability you need. Some correlated features are redundant measurements of the same thing, but others represent distinct concepts that happen to be correlated in the current environment. If you drop a conceptually important feature, you may lose the ability to answer questions stakeholders care about, such as whether a control was active, whether exposure was present, or whether a policy applied. You may also create operational risk if the retained feature is less reliable, less available, or more prone to drift, even if it looks statistically similar today. The exam often tests judgment here by presenting two correlated fields, one that is operationally meaningful and one that is a noisy proxy, and the correct reasoning is to preserve the meaningful concept. When you simplify, you should think in terms of concept coverage, measurement reliability, and decision context, not only statistical redundancy. After you change features or modeling approach, you should validate to confirm that performance and stability improve, because the goal is not just to make the model look cleaner, but to make it behave better on new data. Stability can be assessed by checking whether coefficients, feature importance, or predictions change less across resamples or time windows, and performance can be assessed using appropriate held-out evaluation. It is also valuable to check whether explanations become more consistent, such as whether the top drivers remain similar across retrains, because that consistency matters for trust. The exam expects you to avoid claiming success based solely on training fit, because multicollinearity remedies can reduce training fit slightly while improving generalization and interpretability. When you validate properly, you are treating multicollinearity mitigation as an engineering decision with measurable outcomes, not as a theoretical cleanup. Validation also helps you detect unintended consequences, like removing a feature that was redundant overall but critical for a specific segment. Multicollinearity also complicates causality claims and explanations, and communicating that limitation is part of responsible analysis. When predictors move together, it becomes difficult to say which one caused the outcome change or which one is the true driver, because the data does not provide enough independent variation to isolate contributions.
This is especially important when stakeholders want a simple narrative about what lever matters, because multicollinearity means the evidence supports a combined effect more than a unique effect. The exam may test this by asking what you can conclude from correlated predictors, and the safest answer is that you can predict using the shared signal, but you should be cautious about attributing causal importance to any single correlated feature. Communicating this clearly prevents overconfident decisions, such as cutting a program because its coefficient looks small when it is actually redundant with another feature representing the same underlying effort. When you explain this limitation, you are strengthening trust by aligning claims with what the data can actually resolve. A useful anchor memory for this episode is: redundancy inflates uncertainty. Simplify to regain clarity. Redundancy refers to overlapping predictors. Inflated uncertainty refers to unstable and noisy coefficient estimates. And clarity refers to both interpretability and stability. The anchor helps under exam pressure because it points you away from complex fixes that add more features and towards simplifications that reduce overlap. It also reminds you that the core cost of multicollinearity is not only statistical, it is communicative, because unstable attribution erodes trust in model explanations. When you apply the anchor, you are more likely to choose remedies that reduce redundancy, such as removing, combining, regularizing, or reducing dimension. The anchor is simple, but it captures the underlying mechanism and the purpose of mitigation in one sentence. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.